Okay, now I would like to introduce you a few equations that need to be used when we calculate about something about reciprocating pumps. So pumps can be broadly classified into positive displacement pump and rotodynamic pump. And for reciprocating pump, it is one of a positive displacement pump, which fluid is drawn or forced into a finite space, and then seal it by mechanical means. So from this statement, you understand that reciprocating pump is it will create something that will create a vacuum condition. So means it could suck liquid into a space, and then it force that that liquid into the discharge line, and then this will be carried out repeated in cycle. So the cycle is repeated, and then reciprocating pump, as I shown previously, it can be single acting or double acting. It is actually to increase the volumetric capability. So and a few types of positive displacement pump is is explained previously. So for example, we have a gear pumps, we have lobe pump, and so on. So this is the common diagram of reciprocating pump. So we have we have a piston here. So the piston will be moved forward and backward, and normally this piston is connected with a crank like this, crankshaft like this, and this it will be rotate continuously, and by this rotation, so the piston will move forward and backward. So this, so and then that another thing that you should understand here is, so when this point is at this point, so when the shaft here at this point, so it will create, piston will stay at this point. So and then when it's rotate, when the shaft here is rotate and at this location, so the piston will be pushed to this level. So means that the distance, the area that being created by this piston pump is actually depends on the diameter or the radius of this rotating device. Okay, so this is the first relation that you should imagine about the piston pump. Okay, so why this distance is very important? Because this distance will determine the volume. So as we know that piston pump, it's move fluid by creating a volume. Okay, so means that we need to calculate what is the volume every time the piston pump suck liquid and push back liquid to the discharge line. So, and if you understand this, so means that you know that it is easy for us to calculate the volume for the piston pump by knowing the cross-sectional area of the piston here, and we multiply with time with the height of the stroke motion of the piston stroke here. So, and then this piston stroke is actually closely related to the diameter of this rotating device. Okay, so means that you know how to calculate the volume of piston every time he suck the maximum volume of water before it can be discharged. Okay, so and then another thing that you should know is we have a suction head. Okay, so and then we have a delivery head. So normally we call it as a suction head and delivery head. So what is suction head? So suction head is the height from the level of water at inlet to the center point of the piston pump. So this is the suction head. Okay, so I think you already know about the head of pump that we learned previously in fluid mechanics 1 and fluid mechanics 2. So head of pump means the height of water need to be transferred of a pump. So mean here piston pump only can be run if it can suck or it can bring water from the inlet level here into its own chamber here. Kalau katakan dia tak mampu untuk sedut air dan masukkan ke dalam chamber piston pump, bermaksud piston pump tersebut tidak mampu beroperasi. So at the same time, we have a delivery head. So the delivery head means the height that water need to be transferred. So it is measured from the center line of the pump to the surface of the delivery tank. So this is the delivery head. So and then okay, so in this diagram, so it's written as HMD and we have HMS. So M here means manometric. So you know that manometric means the height that pump could deliver the water. So we call, and in this diagram, it is called the manometric head in suction line. And so this is the manometric head at suction line, and this is the manometric head for delivery or discharge pipe. Okay, both is actually reflecting the same meaning. So and then, so we also learn about the losses in pipe. So previously in Fluid Mechanics 1 and Fluid Mechanics 2 means to make sure that our pump can be used, it must be overcome the friction that occur in our pipeline. So in this diagram, it shows that this is the losses for the delivery pipe, and this is the losses for the suction pipe. So in Bernoulli equation, so we merge all the losses at the output. Okay, but in reciprocating pump, in piston pump, we are not using Bernoulli equation because, so the idea is why we cannot use Bernoulli equation in piston pump, because the flow nature of piston pump is not continuous. So what is the meaning of it's not continuous is, so as you know, when the piston move backward like this one, so it suck water into this space, into this volume, so means there are no discharge. And then when the piston push the water, then the discharge line is now working. So means that it is not continuous flow, so means the Bernoulli equation cannot be used in piston pump. So mean, bear in mind, never use Bernoulli equation in piston pump. Okay, in certain if, okay, later on I will discuss. So after this we have found a pressure vessel. So no, not pressure vessel, we have the air vessel. So later on I will discuss about air vessel. So then so this is the, so means that to overcome, to make sure your piston pump is work, you need to overcome manometric head for discharge, manometric head for suction, you need to overcome the friction. Okay, that is the basic idea in piston pump. Okay, so normally piston pump is work on atmospheric pressure, because we cannot seal this one. In reality, we cannot make sure that this one is actually totally vacuum, absolute vacuum. So means the calculation. So at least we assume that atmospheric pressure is actually works on that, but we try to create a vacuum, means a pressure which is a little bit lower compared to the atmospheric pressure. Okay, so this is the basic idea that you should know when calculating the piston pump or reciprocating pump. Okay, so this is the double acting. So means you know about the double acting. So mean at one cycle, so the suction is occur as well as the delivery is act at the same time. So so I want to explain about the air vessel here. So this is the air vessel. So you know air is gas, okay, but actually it's not containing gas. Air vessel here is actually a tank to receive an extra water from the discharge. Okay, as you know, that might be this discharge is a very big, so a huge volume of water being discharged, but uh, the cross sectional, the pipe here might be a little bit smaller. So mean this water it cannot be compressed. So water is not a compressible fluid. So means that if the water is full at this pipe, so mean the piston pump cannot push the water to flow anymore. So that's why we create an air vessel here as a space uh, that could receive an extra water flowing in this discharge pipe. So and then when the piston is moving downward like this, so when the suction is occur, so as I said, there are no water flow, so all the flow rate at the discharge is become minimal. So when this occur, an extra water at air vessel here will flow into the discharge pipe, and this will make the flow rate at the discharge pipe become steady. Okay, so saya rasa awak dapat imagine kita ada satu extra tangki kat sini. Tujuan dia ialah apabila air dialirkan daripada outlet masuk ke dalam pipe, kadang-kala kita kata mungkin isi padu air yang dialirkan adalah besar. Oleh itu kita akan masukkan air ini secara automatik akan masuk di dalam air vessel sebagai air penampan. Dia sebagai tangki penampan. So maknanya dia akan masuk ke dalam air vessel dan dalam masa yang sama dia akan terus mengalir ke luar. So kemudian pada ketika piston ditarik ke bawah, kita dapati bahawa kadar alirnya agak minimum. Okay, so oleh itu pada ketika itu air di dalam air vessel akan mengalir secara automatik, secara natural, secara gravitational flow. Okay, akan masuk ke dalam air vessel untuk top up mana-mana bahagian yang terkurang. Top up tu maksudnya mungkin ada ruang kosong lagi dalam pipe, so air di dalam air vessel ini akan mengalir ke dalam pipe. So kelebihan ada air vessel ialah aliran di dalam pipe di sini akan menjadi steady. So kita akan bincangkan perkara ini dan di dalam equation juga awak kena berhati-hati kerana sekiranya permasalahan ada berkenaan dengan air vessel, awak kena ubah equation awak. So awak kena sesuaikan pengiraan itu berdasarkan fenomena yang terjadi. Okay, so maknanya ini saya harap awak dapat imagine schematic diagram yang menunjukkan suction head, delivery head, okay, losses di mana, okay, dan kedudukan air vessel. So air vessel boleh dua-dua, sama ada awak nak letak di delivery atau letak di suction. Cuma advantage-nya akan lebih berkesan sekiranya kita letak di dalam delivery pipe. Kerana tujuan dia adalah untuk steadykan aliran. Okay, so kemudian ini yang saya nak terangkan di sini ialah ini. Okay, so maksudnya awak pun boleh faham if one cylinder single acting, so the delivery is only occur when the piston push the liquid. So means that kalau dalam graph, if we draw a graph, so we have a sinusoidal cycle like this one. So means that this is the suction, there are no delivery, so delivery only occur at this point. So that's why engineer will do the double acting piston pump to make sure that the delivery will occur along all the time. So seperti yang ditunjukkan di sini. So for double acting, so the flow rate will flow like this. So mean all the time there are water flowing at the discharge line. However, you could see the graph here. So it is clearly shows that the flow rate is actually start from the minimum to the maximum and then come back to the minimum and then maximum back again. So mean at this situation, the pressure the air vessel, the water at the in extra tank called air vessel will top up the flow rate. So it will top up here. So and then we have an extra volume here and so on and so forth. So finally we could feel that the flow rate is almost constant. Okay, so that's why in this graph you see the y-axis here is in Q. The term is in Q, the flow rate. Okay, I think you could imagine the mechanism of air vessel in piston pump. Okay, so first, this is the a few equation that you should know. So the first is the flow rate. So the flow rate, we could calculate the flow rate by having this equation. Q is equal to ALN over 60. So what is A? A is the cross-sectional area of the cylinder. So you know that we have a cylinder like this, and then we have piston here. So A is the cross-sectional area of this one. So we have an A, and L here is actually the distance from the maximum length of piston. So might be this is the highest point and this is the lowest point of a piston. So this is the length of L. So this is so you multiply the A here, the cross-sectional area, with the L, and then you will get volume. Okay, now you will have volume, but this volume is actually occur at one cycle. So normally in flow rate, we are calculating in terms of meter cube per second. Okay, so and then we need to know the frequency of this movement. So we time with the n here. So n here is the rotation per minute. So because the unit here is per minute, so we need to divide the value with 60 to make sure that we get units of meter cube per second. So please bear in mind that you really understand this equation. So if the equation gives you the rotation per second or revolution per second, so no need for you to divide this that value with 60. So this the divide by 60 is to make sure that our unit is in meter cube per second. So this is for the single acting, and for the double acting, okay, you need to multiply into with 2, because it's will the same volume will be transferred at the same time. So means that the total discharge is actually ALN over 60 times 2. So I think you could imagine how to calculate this one. And then for normally, we will discuss about the piston pump. So if you have problem about the lobe pump, the gear pump, and so on and so forth. So the first thing that you need to do is you need to understand how to derive the equation to calculate the flow rate. So the flow rate is actually the idea of how many volume being transferred in 1 second. So if in piston pump, if you have a gear pump or lobe pump and so on, so it is important for you to know the total volume can be transferred. So for gear pump and lobe pump, there are no specific equation to be used, because it's depend on the design, how many teeth of gear, how many lobe, and so on and so forth. So it's that's why it is we are focusing in this topic for piston pump, because piston pump is quite there is a lot of calculation can be done for the piston pump. So then I would like to introduce you about the efficiency. So previously in fluid mechanics 1, you know that we have a lot of efficiency. We have the manometric efficiency, so we have mechanical and so on and so forth. But in piston pump, so the most important things is we must make sure that our piston can create a vacuum condition and can suck water as many as they would. So means that if the actual volume is equal to the theoretical volume, so mean that is the best piston pump we could have. So means that the first idea of that one is we need to calculate the slip of pump. So the slip of pump, the equation is the flow rate for theoretical minus with flow rate in actual, and we divide into the theoretical value. So and then we time with 100%, and then we could get the percentage of the slip of pump. So slip of pump ni dia akan lebih kepada kebocoran pump. Kita nak tahu berapa persen actually pump kemungkinan akan kehilangan air di sepanjang pergerakan menyedut dan menghantar air. Okay.